All right, welcome to part 3 of section 2, the last lecture of section 2. So, the first topic we will look at in this section is tautologies and contradictions. So, every symbol we have covered in this section so far, just to list them out, we have negation, disjunction, conjunction, implication, and biconditional. Let me try to restart that arrow. These symbols are called logical connectives. So a compound, so we're going to look at another type of statement real quick before we look at tautologies and contradictions. A compound statement is a statement composed of one or more given statements and at least one logical connective. And to compound statements looked at often are tautologies and contradictions. So let's look at what a tautology is. It is a compound statement that is true for all possible combinations of truth values of statements inside it. And a contradiction and just to save writing, I will a contradiction is basically the opposite of a tautology, where it is false for every truth value of the statements inside it. See if we can fix this and then erase this. Since these statements are basically the same with some words changed, just copy and paste that. And that's a contradiction. So let's take a look at an example of this. For the compound statement P disjunction not P and P conjunction not P, or negation of P. So we have P not P. We'll construct a truth table. This is only one statement, so we only have two values to look at. So, of course, have the opposing truth values. So the disjunction of not P will always have a truth. It's a tautology because it's always true. And then the conjunction of P and not P is always false, which makes sense because they have opposing truth values. All right, let's look at the next topic. And the next topic we will be discussing is logical equivalence. So when two compound statements have the same truth values for all combinations of truth values for their respective statements, they are said to be logically equivalent. So let's look at an example of this. Say we are given the compound statements Q implies P and Q implies Q conjunction P. So let's construct a truth table here. And remember, like I said in the end of the last video, when looking at biconditionals, that we will look at all of the respective statements that make up the compound statement, or statements that we're looking at here. And these are all of the respective statements that we will need to look at for this. It's going to be for different columns. Then the conjunction of Q or P. Then we will look at Q implies P. So if you remember, for an implication, it is only false when the statement that is being implied is false. So it's only, and the one that's leading to the implication is true. So when Q is true and P is false, Q implies P is false, but everything else is true. But let's look at this implication. Q implies Q conjunction P. Well, both statements are true, so they are true. Both are false, so they are also true. And in this one, we have Q is true and Q conjunction P is false. So the statement being implied is false, but the one leading to the implication is true. That's false. And they're both false again. So Q implies P and Q implies Q conjunction P are logically equivalent because they have the same truth values for all possible truth value combinations of the respective statements that make them up. All right, so there are important laws or fundamental properties that have been developed using logical equivalence. And such laws are, say we look at 3 statements. P, Q, and R. We have communicative laws. So, an example. P's disjunction Q is equivalent to Q disjunction P. Another one is associative laws. So an example of this. P conjunction of Q conjunction R is equivalent to P conjunction Q conjunction R. And it's basically moving the parentheses around and grouping things together. And for the communicative laws, it was swapping the statements around. And 3, distributive laws. So if we have P disjunction Q conjunction R, that is logically equivalent to P disjunction Q, the conjunction with P disjunction R. And basically what it's doing is distributing P disjunction into the statement Q conjunction R. And yep, so fourth one is De Morgan's laws. So an example of this, we have not P conjunction Q, that is equal to not P disjunction not Q. So basically what this law is saying is that this compound statement is logically equivalent to the these conjunction statements can be split into the disjunction of their components. And the way all these laws can be determined if you were to put these statements into a truth table and look at the truth values of them, you would see that they're logically equivalent to each other. So if you want to do that, you can do that on your own time. But we're going to move on to the next topic for this lecture series. And that next topic is going to be quantified statements. So statements are quantified when specific conditions, which often are from sets, can define them. Quantifiers are the definers of these conditions. So the most often used quantifiers, there's two. We have the universal quantifier, which is denoted by this symbol, and this is phrased as for every, for each, or for all. So basically this quantifier says that every condition defined for the statement is met. And then the second one is the existential quantifier. And this is denoted by this symbol, a fancy backwards looking E. And this is phrased as there exist. Hence why it's called the existential quantifier. And it's basically saying that this does meet a condition, may not meet all the conditions that are defined, but it does meet at least one. So let's look at an example. Say if we are given this set A, which is equal to which has elements 6 and 12, then P of x equals 2x plus x over 3 is even for each x that's an element of A. So this is an implication, and let's break these two statements, or let's plug in the conditions from the set A to verify that this statement, or to see if this statement meets all the conditions. So if we plug in 6 into the open sentence, we will have 12, and then we have 6 divided by 3, which is 2, so that's 14. which is even. And if we plug in 12, we have 24, and then 6 divided by 3 is 4. That gives us 28. That's even. So we can quantify this statement as, and we'll use the universal quantifier because every condition, every element that's an A satisfies the implication that P of X is even. So we are using the universal quantifier for this. All right, so the last topic we will look at in this lecture, and for section 2, pick out a color here, just for a different topic, is characterization. So if you remember from the last topic covered in the last lecture was biconditionals. And also remember that a biconditional is the conjunction of an implication and its converse. So one statement that could be used to define the other if a quantified statement can define a biconditional between the two. And this is a definition of what a characterization is. So this statement can then be defined as a characterization. So I know that this may be a lot of words and you may be trying to wrap your head around what this means, but we're gonna look at an example here that I hope will make this definition of what a characterization is a little bit clearer. So we're given the statement L is the English alphabet if and only if L is equal to this set A, B, C, etc. up to Z. So basically basically it's understood that this is a set of the 26 letters of the English alphabet. So let's break this down and look at the statements that are being stated here. So we have P of L. L is the English alphabet. And then we have Q of L, or we'll call it Q of L, which is just L is 26 letters of the alphabet, of the English alphabet. So let's look here. We could construct a truth table, but I believe you've seen plenty of truth tables about this. So we can just logically reason out here that this biconditional is true. So therefore, for all of x, that's an element of L, Px implies Qx is true. So therefore, we can just say that Qx is a characterization of this statement. And so basically we can just state Q of L. L is the 26 letters, and that can just automatically imply that it's the English alphabet. And that's a characterization. So that is it for the Section 2 lecture notes. I'll just do another fun little characterization. Change colors here. We'll use one of my favorite colors, light blue. So let's do another characterization here. Let's say that T is fun if and only if T is mathematical proofs lectures. So this is just something that I hope you've been enjoying if you've been watching this series, or even if this is your first video to watch, that this biconditional of course, there really is no solid logical argument for this, but I would like to believe, and hopefully you would too, that these are both true. However, the funny thing is that if both are false, technically this biconditional is true as well, but that these mathematical proofs lectures along with the examples characterization of fun. All right. Yeah, but I hope that you've been enjoying these lecture series, and we've now officially finished the fundamentals. And of course, we'll work some examples for section 2, and then we'll start looking at proof techniques after that. So, guys, thank you all so much for watching. Really means a lot to me that y'all are taking the time to watch these lectures, and I hope that this has been beneficial for you and that maybe you might find enjoyment out of them. Maybe these lectures can be a characterization of fun for you. So, all right, thank you guys, and I'll see you in the examples for section 2.